So hello everyone, my name is Pia. So today I'm gonna talk about what is IO and its application. I'm working with the Machina IO, which is one of the new projects that research and engineering on the IO, which is indistinguishability obfuscation, supported by the PSC EF. So let's start from here. You might heard of some trustless applications like Bitcoin and Ethereum bridge, or encrypted mempos, or private voting, private auctions, zk-TLS. But I like to emphasize that is this actually a trustless? Most of them are relying on the security, whereas threshold-based threshold-based cryptography, which is usually implemented by the multi-party computation or multi-key FHE. Luckily, we actually have a theoretical solution for this, which is indistinguishability obfuscation. So you might then raise a question about why this is a problem, how this indistinguishable obfuscation can solve this. So today, I'd like to talk about start from limitation of current trustless application and what is actually an IO and what can be the application of this IO can unlock and our contribution and the progress on the Machina IO. Okay, so let's start from this example. This is one of the application that I mentioned before about Bitcoin and Ethereum bridge. And I'm gonna dive deep into this example to show you what is the current limitation and what this IO can do differently. So start from the notation. This guy, red guy, is the adversary who can do the malicious stuff. For example, malicious stuff means if they obtain a Bitcoin key, they can just withdraw the fund from the wallet without any restriction or policy or rules that following this Bitcoin and Ethereum bridge. The blue guy is the honest party, which is will do the expected behavior when they obtain a key. They will basically check if the user actually holds a proof of burn the WBTC on the Ethereum and then use this key to generate the signature to do the transaction. And this is just a key, and you can make a transaction and you can withdraw the fund. Easy. This is the notation of Bitcoin and Ethereum bridge. So the traditional approach is a multi-party computation, which this key is, as you can see, very important because you can just generate a signature and you can just make a transaction out of it. So previously, we divide this key into the multiple pieces, and then we distribute this to the multiple parties. But actually, these parties, we don't know whether this will be behave maliciously or honestly. What does this problem? Let's say all the pieces are grabbed by the malicious parties, then basically you could retrieve this Bitcoin and Ethereum bridge will be no longer sound anymore. These malicious parties can just generate a signature and then withdraw the Bitcoin without restriction. You might ask a question, what if we just increase the number of the number of key distribution? Or what if we just increase the threshold? The issue of the multi-party computation is basically when you want to do the computation at the same time, all the parties of the threshold should stay online. This is the liveness assumption of the multi-party computation, which basically makes this application very inefficient if the threshold size is large enough. So this is the obfuscation can fix this. So basically from the example that we just talked about Bitcoin and Ethereum bridge, obfuscation, you just make a program that hides the key inside of it and get the proof of the Ethereum's burning transaction and check if it actually burned on the Ethereum side and then generate the signature and then make a transaction for Bitcoin withdrawal. This is maybe a little bit confusing for now. I'll explain it multiple times with the same example, so don't worry. And the cool part of the obfuscation is that even though the adversary grabbed the whole obfuscated program, they cannot even no longer do the malicious activity. So okay, what is obfuscation? This is a general definition of obfuscation, where you could just imagine it as a program compiler. Let's say there's an original program P, like on the previous example, we talked about like Bitcoin, Ethereum, like bridge program. And obfuscation is you compile this program into some obfuscated program where you cannot see the internal logic inside. However, it behaves exactly same as the original program P. So when you insert the input X, you would always get the same output, whether this is CX or like obfuscated CX. It's clear, right? But here's the useful thing. This is the useful mental model of the obfuscation that like you might wonder, like why obfuscating a program is actually useful, like where people can use it. So this is a key-based obfuscation where in Machina IO, like our scheme is kind of relying on, but this is very simplified interface. The obfuscation includes like the full scheme includes the two-step. One is the obfuscation step, which basically you have your program have a public function f that inside there's a secret key k that only exists on the obfuscator side, and then basically obfuscator obfuscates this and then obtain this c tilde, which is obfuscated program. And this obfuscated program can be fully public, and then you can just like publish on the Ethereum, like you can publish on like some very public places, and the obfuscator can totally disappear. This process is very like totally non-interactive, where obfuscator and evaluator will not interact at all. Okay, the next step, evaluation. Evaluator obtain the obfuscated program, which is C tilde, because it's a public, you can just download it anywhere. And then basically, evaluator provide their own arbitrary input X for the program, and then they evaluate, and then what they can obtain is F evaluated over the secret K and X. However, they still have no idea about what this K looks like. If you're a little bit familiar with the cryptography, this is kind of a similar idea with the functional encryption actually. However, and also, one of the cool part is that this two-step is totally non-interactive, and also this evaluation step is binded to the F, which is distinguishable point with the FHE, where when you evaluate stuff in the FHE, you cannot like ensure that the evaluator is actually evaluate over this specific function, where IO scheme, you're very binded to the F. Okay, so this is a little bit technical. I'll now go back to the like previous example and connect these dots together. So within this mental model, useful mental model of obfuscation using key-based obfuscation, you can just now recap this Bitcoin and Ethereum bridge example where the public function f is a conditional signature program. Basically, what this program will behave is that if the given proof, like given input x, contains the proof of burning the WBTC on the Ethereum, because when you are bridging stuff, you first have to like burn it and then you can redeem it, right? So you really make sure that this is valid, and then they can generate the signature. This function is generating a signature. If this proof is valid, and this will withdraw the Bitcoin from the hard-coded, from the Bitcoin wallet. And still, the evaluator, because the C tilde is totally obfuscated, even though they're using this function, even though by providing their arbitrary input, which is proof, they have no idea about original Bitcoin secret key. This is very useful, right? Because you can just publish the program that contains the key where you have no idea about the key, but everyone else can just use it, download it from the public. Yeah, this is the obfuscated mark. So the evaluator cannot see like the K looks like. Okay, so what are the applications out there? Basically, the key idea of obfuscation can unlock is you can encode the specific like secret data within the specific secret program and allows others to use it without any interaction. And the example that we take a look at right before the Bitcoin Ethereum bridge, this specific secret can be like Bitcoin key, wallet key, and the specific program can be like conditional like signature like function. And you who are the obfuscating person is an obfuscator, and others is the evaluator. So I hope this dots got connected. And then, yeah, so basically you can do like private non-interactive computation where like secret is hard-coded and anyone else can like execute the program, which is makes the trustless applications become really trustless without any reliance of the security assumption of a like threshold-based cryptography that we talked just now. So yeah, this idea is super cool. Basically, you might saw this blog post, Vitalik's like Ethereum possible future. In here, there's like a 3 card, which is ZK snark, FHE, and then obfuscation. Within this like a huge component, like IO can take a part of the Ethereum like roadmap in the critical like parts. However, of course, this is not just like a magic sword. Like to achieve very hard thing, you need to have like basically it's like super hard so that it can have a very powerful like feature. So these are the comments on the IO. Like many people are doubting about like is it actually real? It seems too good to be true. Like is some people are like too difficult so that like they just abandon it for a while. So now is our contribution part, where we in the Machina, Sora, Enrico, and Pia are trying to move this IO, which is super cool, from the theory to the practice. And we publish papers and write some code. So first, we actually suggested publish the straightforward IO construction, Diamond IO, at this year February. And second, we actually completed the end-to-end implementation of this Diamond IO construction scheme with the secure parameters. And this is the some ideas that how much we achieved from the existing state-of-art result, which is previously based on this paper. From the obfuscation to evaluation, it took more than like 10 power 27 years to, in our like sufficiently secure parameter on the current repo test, it takes less than 1 hour for the obfuscation to evaluation. Yeah, but still we have a lot of challenge to be solved. Like for example, our like latest test success is around 1 input bit with the 60 AND gates, which ideally, just like how much the ZK come from the theory to right now as a production, we also want to make this IO very practical so that people can unlock this like multiple trustless application into actually trustless. So these are the 2 goals that we are focusing on. Like first is we want to make the input size larger, so that ideally, at least we want to accept the 10 kilobyte of the input of the circuit. Why 10 kilobyte-ish is we want to accept the ZK snark as a proof so that we can extend this IO to the arbitrary other computation like FHE or like ML. And the second is like generally we want to make this circuit logic more complex but still practical as possible. Yep. Okay. So is something that I prepared so far. I prepared some Q&A slide in case if anyone have a question.
First question. Oh, thank you. So the first question was if there is anywhere I could find a presentation. And the second one, because I missed a lot and joined late, but is it based on garbled circuits and oblivious transfer? Is it the concept of the obfuscation under it?
So the obfuscation is a general definition, and just like the ZK snark can also rely on different security assumptions or the implementation. IO can also implement it in various way, and in our approach, we actually use the FHE and BGG encoding. We use this approach for implementing our IO construction, not the Garble circuit or the MPC one. So there might be potentially, could be other constructions that can base on what you mentioned, but in our case, it's no.
Okay. Yeah, thank you. And with regards to the first question, is there anywhere I could find the presentation?
I'm not an event organizer, but I would like to share the presentation in public. Maybe I can post on the Twitter.
Yeah, sure.
Yes.
Thank you.
Twitter or some group chat.
Yeah, that would be great.
Yeah. Okay.
Where can I find the GitHub that you featured in the presentation?
It's open source. You can just search Diamond.io.
Okay.
We haven't announced it yet because actually the end-to-end test with the secure parameter was not passing up to 5 hours ago. And we actually make it happen today. So I edit the slide at the last moment. So basically that's the reason why we haven't announced the GitHub yet. But we'll also we prepare a very a detailed tutorial or the 0 to hero version of IO as well on our blog post. So yeah, I hope we can share more and follow the Machina IO on Twitter. I actually haven't added anything on the slide, but yeah. Yeah.
Thank you. Congrats on the test passing.
Thank you. So yeah, thank you for listening. And more question, reach out. Yeah.